Here we are talking about exponential growth and decay. We want to sort of talk about what these mean, what they look like, do some problems with it, and we're going to escalate this really quickly. As always, lesson is brought to you by Conalonzo Inc. We're here to help you with all of your math needs. The goals for this lesson are to be able to set up an exponential growth or decay equation as well as to solve an exponential growth or decay equation. A big part of the solving is also to be able to accurately use your calculator to evaluate what needs to be figured out. So make sure that you have a calculator handy in addition to the notes that you're writing down. Make sure you get all of these formulas written down because they're very, very important. And away we go. When we talk about an exponential function, it's always in the form of y equals b to the x. B is the base, x is the exponent, and y I'm going to call the answer. There's not a specific term for it. But this is going to lead into something we're doing later on. So I'm going to call y the answer for this, okay? So we always have a base of a number to an exponent, which is x, and that is always equal to some sort of answer. We've been kind of solving these equations already, 2 to the 3x equals 8 and figuring out what it is. But this gets a little more complicated when we're talking about specific exponential functions. But they will always be in this form. An exponential function can be either growth or decay. And there are some differences between the two, okay? Growth always increases over time, while decay always decreases over time. Growth always has a base larger than 1. So you might see something like 2 to the x power, 2 being the base, that's larger than 1. A decay, meanwhile, has the base that is smaller than 1. So you might see something like 1/2 to the x power. Now notice there's an asterisk here. And we look down here, the base is always positive, which means that it's greater than 0. So you cannot have a negative base. So when we talk about a base smaller than 1, what we really mean is a positive base smaller than 1. So 1/2, 1/3, 2/5, 7/9, etc. An exponential growth will have a graph that goes up, and an exponential decay will have a graph that goes down. So that's kind of what they will look like on the coordinate plane. Okay, so they're two sides of the same coin. Growth is increasing, goes up, has a base that's larger than 1. Decay is decreasing, goes down, has a base that is smaller than 1. But remember, the base is still always positive. The negative, that you cannot have a negative base when we are talking about exponential functions. So is an equation growth or decay? Let's figure it out. Looking at this first one, y equals 1/5 to the power of x. We want to look at the base, which is 1/5. Is that greater than 1 or smaller than 1? It is definitely smaller than 1, which means that this is a decay function. Letter B, looking at the base, which is the number in the parentheses. 3 is the coefficient, 4 is the base. That base is larger than 1, therefore this is growth. Letter C, again, looking at the base, which is in the parentheses, 1.2 is a number larger than 1, so this is also a growth equation. Remember that we're always looking at the base, that's the one that's attached to the exponent, and it tells us whether it's growth or decay based on whether the number is smaller or larger than 1. Notice none of these actually have a base of 1. If you have a base of 1, it's not an exponential function. So it's either smaller than 1 or larger than 1. That tells us if it's growth or decay. Exponential growth equations always have a formula, and this is the formula that we use, y equals a times 1 plus r to the t power. Each of those letters signifies something. So y is your final amount and a is your starting amount of whatever is growing exponentially. So maybe that's bacteria. A would be the number of bacteria you started with, y would be the number of bacteria that you end with. It might be people in a population, it might be rabbits, it might be I don't know, any sort of thing that grows exponentially. A would be your starting amount. B would be how much you end with. R is your rate, and your rate always has to be put into the equation as a decimal. So rate is often given to us as a percent. Say we might be told it grows 18% each year. When putting that into the equation, however, we have to do 0.18. We have to change this to a decimal, which is not terribly tricky until you get something like 3.5%. Remember that when you're changing that to a decimal, it's not 3.5, it is 0.035. You're always moving that decimal point 2 places to the left in order to write a percentage as a decimal. So be really, really careful about that rate. It skews your equation quite badly if you do not put that rate in as the proper decimal. And then T is always units of time. Make sure that your units of time are the same. For example, if something is growing so much every hour, and then it says how much will you have in 10 days, make sure that you then convert that to hours, okay? Your units of time always have to be the same. Most of the time they will, but just check to be sure that it's not, growing every day and you're being asked to find how many months or how many years. Just be very careful about that. So this is our growth equation. We're going to put it into practice with a couple of problems. I'm just going to rewrite that so we can see it. Mrs. Khan's house is determined to appreciate at 8.3% each year. If she bought the house for $95,000 in 2013, how much will it be worth in 2020? So we've got a lot of information here about Miss Khan's house. We know that it's growing in value because that's what the word appreciate means. Appreciate means that the value is growing, and it's usually an exponential because it's growing at a certain percentage rate, which in this case is 8.3% each year. Now there's our unit of time, okay? We're looking at years. So if the house was bought for $95,000, how much will it be worth in 2020? Let's start filling some things in. So we know that the 95,000 is how much the house started out at. So we're going to put that in for our starting or our initial amount, letter A. 1 is always just 1. We know the rate of appreciation is 8.3%. Remember, we moved the decimal point 2 places to get the decimal. So it's 0.083. And now we need to know our time. Well, the house was bought for $95,000 in 2013, and we want to figure out 2020. That's 7 years. Now I'm just going to check and make sure my rate was per year, my time is in years. I'm good because my unit of time matches up. Okay. My final amount is Y because that's what I don't know. That's what I want to figure out. How much money is this house going to be worth in 2020? We're going to evaluate, and this is where your calculator comes in. You have to be very careful to enter the steps in a specific order, and we're going to use order of operations. So let's start with the parentheses, okay? So we're going to start by adding 1 plus 0.083, which is 1.083. After parentheses comes exponents. So we're going to take 1.083 to the power of 7. Remember that on your calculator, you're typing in 1.083, use that power button of 7 and hit enter. You should get 1.7474, etc. Do not clear that from your calculator. Leave it on your calculator. Don't round it, don't anything. Leave it on your calculator and then multiply by the 95,000. So times 95,000, make sure you get the 3 zeros and hit enter. This gives you the worth of the house, which is $166,005.62. We always round money to 2 decimal places. So I'm going to round that to a 62. It's very important when you are doing these problems that you do not clear your calculator and you do not round in the middle of the problem. If you do, it will cause what's called round off error, and you will not be as exact or precise or accurate as you should be. And most of the time you'll be off from the answer key, which is what your teacher grades you by a significant enough amount that you'll get it wrong. So try to leave your work all on your calculator and just keep adding the steps as you go, and then round when you get to the very, very end. This is generally a really good practice in math. When we're dealing with decimals and such, we always want to be as accurate as possible, and rounding within a problem is not accurate. So try to keep it all on your calculator, and we'll keep practicing the keystrokes so that you can be as accurate as possible. All right, our next problem here, let's make sure this one is a growth. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells. Sounds like growth to me. Thus, doubling. That's going to be important that it's doubling. If we start with one bacteria, which can double every hour, there's my unit of time, how many will we have at the end of the day? So let's go with what I know. I know this is going to be a growth equation, so I'm going to write my formula down. I know the starting amount of bacteria is 1. And I do not know how many I'm going to end with. That's what I want to find. Now, my rate is doubling. If you think about that, that means that growth is 100%, because every hour I have 100% more than what I had previously. 100% is 1. Remember, we're moving the decimal point 2 places. So 100% is 1. So that's what I'm going to put in for my rate. Now my time, I am growing this every hour. And the question is, how many will we have at the end of the day? Well, a day needs to be turned into hours. One day is 24 hours, so that's what I'm going to put in for my T. I want to start this by working in the parentheses. I'm going to start with 1 plus 1 is 2. Then I'm going to take 2 to the power of 24. And I'm going to get 167777216. Multiplied by 1 is the same thing. So I don't really need to multiply by 1. I'm just going to take my number, make sure I get the right amount here, and I'm going to get 16,777,216. And what are we talking about here? Because remember, we always want to label as well. And we are talking about bacteria. Remember on the last one too, now you might have not have noticed because I didn't say anything about labeling, but I put that dollar sign. That's my label. Okay, so when we're talking about money, we're using a dollar sign. In this case, we're talking about bacteria, so I'm going to label this bacteria. That is our exponential growth formula. We also want to talk about exponential decay. Decay is a formula very, very, very similar to growth, except that it uses a minus sign instead of a plus. Everything else is the same. Y is your final amount, A is your starting amount, R is your rate, T is your time. You're putting everything in the same way. It's just that you're going to be subtracting instead of adding. So let's walk through a couple of these. An adult takes 400 milligrams of ibuprofen. Each hour, the amount of ibuprofen in an adult system decreases. Now, this is how I know that it's decay, by about 29%. How much ibuprofen is left after 6 hours? So let's fill into this decay equation what we know, okay? We know, let's start with the 400 milligrams. That's how much you're taking. So that's the starting amount of ibuprofen. We know that it decreases at a rate of 29%, which is 0.29. And the question is, how much is left after 6 hours? Y is our final amount. That's what we don't know, and we're going to find. So here's where we can kind of just plug this into our calculator. We're going to start with 1 minus 0.29, which is 0.71. Then I'm going to take that to the power of 6, which is 0.128100284. So remember, I'm starting with my parentheses, then I'm taking it to my power, then I'm going to take that number times 400. I'm doing all of this on my calculator, and I'm ending up with 51.24 milligrams. So after 6 hours, an adult would have 51.24 milligrams left in their system. That means that it's probably time to take another ibuprofen, which it makes sense since they tell you about 6 hours you're supposed to take more. So what someone has done when they're figuring out the dosing and such is how long does the dose last, how long does it stay in your system, etc., and when do you need to take another one. That's what this is telling us. After 6 hours, we're left with a little over 50 milligrams of ibuprofen in our system. Notice I did all of that on my calculator. I did not round till I got to the very end. Let's try another problem about depreciation. You buy a new laptop for $2,100. The laptop depreciates, remember that's another word for decay, by 45% annually. What does annually mean? If you're not sure about that word, let's define it. Annually means every year. Ev- that doesn't make sense. let's write this word again. How about we just say yearly? That might make more sense. So every year, this laptop is decreasing by 45%. How much is the laptop worth after 2 years? So we want to know, after 2 years, decreasing by 45% each year, how much is this laptop going to be worth? That's our final amount. We know the rest of the stuff, and we're going to fill it into our decay formula. So the starting amount for the laptop is $2,100. The rate that it depreciates is 45%, 0.45. I hope you're remembering to change your percent into a decimal and that you're doing it correctly. And then the question is, how much is it worth after 2 years? 2 years would be our time. So let's evaluate this. We're going to start with the parentheses, and we're going to take 1 minus 0.45, which gives us 0.55. I'm going to write this down so you can see it, but I'm also just typing this into my calculator. Next, I'm going to take this to the power of 2, which is 0.3025, and then I'm going to multiply by 2,100. And I end up with $635.25. So this laptop that you paid over $2,000 for after just 2 years is only worth a little over $600. That's kind of crazy to think about how quickly those depreciate. But it also kind of makes sense. They're always coming out with new tech and laptops that are faster and more memory and all kinds of different things, right? So after 2 years, it's pretty obsolete. Same is true of cell phones and other electronics. So it makes sense that it would depreciate by almost half every single year. Now, make sure that you understand your vocab. One of the things we're talking about here is vocab and what do these mean? You should know that the word annually means every year, that you're working in time of years. I hope you're also understanding how to plug everything into the formula, as well as how to evaluate it using your calculator. Now, one of the big things we look at with exponential growth or decay is interest. And the formula for interest is slightly different. Growth is still a plus and decay is still a minus, okay? However, usually we're talking about growth of money in an account, and the formula is a little different. We still have our final amount, but this time it's A instead of Y. We have our principal amount, which is the amount that you are investing. So that's the amount that you're putting into your account or your stocks or whatever. Still the 1 plus, but this time you have to take the rate divided by the number of times it's being compounded. And then the power that we're dealing with is time times the number of times that it's being compounded. So when you put your money into, let's say, a savings account, you earn interest on that money, and it's compounded different times. A lot of savings accounts are compounded quarterly, which would be 4 times a year or every 3 months. So every 3 months you are paid interest. However, let's say you put your money into this account and you're getting 2% interest. They don't pay you 2% interest every 3 months. They pay you 1/4 of 2% interest every 3 months because you have to divide that 2% APR, which is annual percentage rate, by how many times it's being compounded, okay? Now, credit cards, they compound your interest monthly. So they talk about like 19.5% APR. APR is your annual percentage rate. They talk about that with cars and buying a house and all kinds of stuff. Anytime you're borrowing money, there's an APR. That is divided by how many times it's compounded. So if you're paying, let's say 19% interest on a credit card, that's not 19% every month. It's 19 divided by 12. every month. And then that's on your balance of money that you have, which is your principal amount. Okay. So we're going to do a couple of problems that relate to money specifically and how we use this formula. So you want to open a savings account with $100. That's going to be your principal, by the way, that you got for your birthday. Your bank offers the following savings account options, which will give you the most money after 5 years, assuming you do not deposit or withdraw any money. Let me rewrite this formula here. So P is our principal amount. We've got $100 we're going to deposit. And R is our rate, which in this case is 4% compounded annually. Annually means one time a year. So 4% is 0.04. And we're going to divide that by how many times per year it's compounded, which in this case is 1, because it's only one time per year. Then we're going to take our exponent, which is NT, N being 1 again, because it's compounded one time a year. And we're doing this for 5 years. So T is 5. And we're going to plug all this in and we're going to figure out how much money will we have in our account. So again, let's start in the parentheses. 1 plus 0.04 is 1.04. I didn't really have to divide the 0.04 by 1 because that's itself, right? And I'm also going to multiply my exponent at the same time. 1 times 5 is 5. Now I'm going to take the 1.04 to the power of 5, and I get 1.2166, et cetera, et cetera, et cetera, which I'm then going to multiply by 100, which tells me that I will have in my account after 5 years $121.67. So after 5 years, I've made a little over $20 on this account, assuming I haven't deposited or withdrawn any money. Okay, that's option 1. Let's see what else the bank is offering. The second option is 2.5% compounded quarterly, which is going to be 4 times a year. We're going to use the same problem or same formula. We're still starting with $100, so that's our principal. Whoops, and I wrote it in the wrong spot. There we go. Our rate this time is 2.5%, so that's 0.025. Remember, we're moving the decimal place 0.2 places. And we're going to divide that by 4 because we're compounding this 4 times per year. My power is going to be N, 4 again, times my time, which is still 5 years. I'm still working on the 5 years, okay? Now I'm going to evaluate. So I'm going to start with 0.025 divided by 4 plus 1 gives me 1.00625. I'm also going to multiply 4 times 5 in the exponent to get 20. Now I'm going to take the 1.00625 to the power of 20, which is 1.132, et cetera, et cetera, et cetera, times 100. This gives me an amount of $113.27. So this time I've only made $13. So going back to my previous one, I had $121 in my account. So far, it seems like that's the better option to do the 4% compounded once a year. But the bank is offering one more option. Let's see what it is. Now we're going to compound 1.2%, but we're going to do it monthly. Monthly, remember, would be 12 times per year. Let's put this into our formula. Our principal, remember, is still the $100 that we got for our birthday. So we're going to start with $100. And we're going to multiply this time. Our rate is 1.2%, so 0.012 divided by 12. I'm compounding 12 times a year. 12 is also my n in the exponent times my 5 years, which is how long I'm figuring this for. And that's going to give me the amount in my account. Let's start in the parentheses. I'm going to take 0.012 divided by 12, which is 0.001, and I'm going to add 1 to it. I have 1.001. And then my exponent, 12 times 5 is 60. Now I'm going to take 1.001 to the power of 60, which is 1.06, etc. And I'm going to multiply that by 100. And I end up with 106.18. So this time I only made $6 over 5 years. So clearly my best option was to do the 4% compounded annually, which tells me that the higher the percent is better than compounding more often. Okay? So when you're looking into an account, the higher your percent is, the more money you're going to end up making. Now, obviously, when we have an account, we also want to be continuing to deposit money to grow our balance or grow our principal, which in turn grows the interest that we earn. But in this case, we're just figuring out what's the better option. It would definitely be the 4% compounded annually. One more here. Your parents started a savings account when you were born. They invested $2,500 at 3% annual interest, compounded quarterly. Remember, quarterly means that that would be 4 times a year. They plan to use this investment to pay for your college tuition. How much money will be in the account when you're 18, of course, assuming that they did not deposit or withdraw any money? So let's start this out. So we know that our principal is $2,500. And we want to find out how much is going to be in the account after 18 years. Our percentage rate is 3%, so 0.003, right? No, 0.03, I'm sorry. See, and even I make mistakes sometimes with getting the right percentage rate down. We're going to divide that by 4 because it's quarterly. Our N here is also 4 times 18 years because you'll be 18 when you graduate from high school and want to use that for college. Let's start evaluating. We're going to start in the parentheses and we're going to take 0.03 and we're going to divide that by 4, which is 0.0075 plus 1. 1.0075. And then we're going to take 4 times 18, which is 72. 1.0075 to the power of 72 is 1.71, etc., times the $2,500 initial investment. And that means that in this account, when you turn 18, it's $42.81.38, which is not a whole lot of money to pay for college. That's why you kind of want to be adding to it as you go. You don't want to just put some money in there and let it ride. You really want to keep adding to it so that, again, you can grow that principal and make more money. I hope this has been educational for you, both in learning about different topics and helping you figure out how to set up and solve an exponential equation, as well as to use your calculator correctly. We're going to keep practicing with this. We're going to keep reading, looking for information, putting it into the growth or decay formulas, and we are going to use our calculator to evaluate. As always, this has been brought to you by Con Alonso Inc. We offer math lessons with pizzazz. We hope that you're learning a lot, and if you have any questions, please be sure to let us know. Take care.